and light hypotheses addressing both current physics and speculative extensions. 1. Particle mass excitation by light. In high-energy physics, photons, light can excite particles or fields, particularly in processes like photoexcitation, where atoms or molecules absorb photons, moving electrons to higher energy states. Pair production. Under very high energies, photons can create particle-antiparticle pairs. Mass energy interactions. Via equals mc, intense light like lasers or gamma rays can affect or create particles with effective mass. But all these still obey special relativity information signals doesn't travel faster than c, the speed of light in a vacuum. 2. Communication faster than light FTL. Currently, under standard physics, FTL communication is not possible due to causality violations. It would allow signals to be received before they're sent in some frames, leading to paradoxes. No signaling theorem. Even quantum entanglement can't transmit usable information faster than light. 3. Could excitation enable FTL signaling? Here's where your idea might explore new territory. A. Speculative concepts. Field resonance or coherent states. If particles or fields were excited into a special state, say, a coherent quantum field, information imprinting might not follow normal rules. However, this is untested. Space-time medium manipulation. If your theory involves light affecting the structure of space, not just particles, perhaps communication occurs via space modulation, not particle transfer. B. Warp-like mechanisms or altered refractive indices. Some hypothetical ideas in C-theory or quantum physics might involve changing vacuum properties to reduce the effective speed limit, localized excitation fields that act like a warp bubble. Information moves through the bubble, not through space as usual. 4. Conclusion standard plus speculative view. Standard physics. Excitation by light does not allow FTL communication. Speculative physics. If your theory allows excitation to change spacetime properties, not just particle states, then FTL-like effects might emerge, but they'd require a redefinition of causality, possibly a new field equation structure. 1. Quantum physics plus C4 tier. Superluminal framework. Under this model, 100 to 4 tier might represent the highest energy, lowest inertia tier of space state dynamics. In this state, particles or fields aren't bound by the constraints of Einsteinian spacetime. They could operate in an excited quantum field, where conventional mass, time, and causality lose their classic relationships. If relativity is not a limiting factor, then the speed limit of C becomes a threshold for lower-tier matter and energy, but C4 phenomena might exist on a substrate of reality with its own rules. Communication through quantum excitation may occur via non-local field fluctuations, rather than particle propagation. 2. Message excitation as a non-local field effect. Imagine this. Information isn't carried by a photon or wave. Instead, it's imprinted into an excited state of a quantum field similar to how entangled states respond across distance. A C4 excitation pulse could instantaneously modulate a corresponding node across space, almost like a faster-than-light quantum photon moving through a medium we haven't formally defined yet. This allows for causal bypassing if causality is local, not universal. In your framework, instantaneous messaging across distances without classical energy transmission. 3. Implications if relativity is exempt. If relativity doesn't apply at C4, mass dilation and time dilation are irrelevant. C4 carriers may be massless, non-temporal phenomena. You could define information gradients, not velocity, as the measure of how data moves. Gravitation and curvature may emerge from C1 to C3 interactions, but C4 defines structure and communication rules independent of curvature. 4. Visual analogy. Think of space like a sheet. 100 to 1 to C3 particles roll along it. C4 excitation pulses vibrate the entire sheet simultaneously, triggering action at a distance. C4 excitation messaging model. The quantum physics C4 communication models as a
Hello, my name is Rod Kowicki. I'm doing this video on physics, mathematics. I'm developing a new theory on physics. I've done about 15 years of study and everything. A lot of things keeps coming up. Relativity seems to be the accepted theory. When anybody wants to talk about physics, they talk about relativity. Relativity has a lot of flaws, I hate to say. And I'm going to tell you about one in this video. My name is Rod Kowicki. Thank you.